So a force of static friction can be as big as it needs to be to prevent slippage, up to a point. We would like to be able to predict and calculate that breaking point. We'll use the Coulomb model of dry friction to write down an expression for the maximum force of static friction. And in this model, the strongest that static friction can be depends on two factors. The composition and texture of the two surfaces in contact and the magnitude of the normal force between them. Not the pressure per se, but the normal force. What we're saying here is that the maximum force of static friction is directly proportional to these two factors. Put into a descriptive word equation, what we're saying is that the magnitude of the maximum force of static friction is equal to the roughness or stickiness of the combination of surfaces times how hard they are pressed together, by which we mean the magnitude of the normal force. So we need a way to quantify this right here, the stickiness of the combination of surfaces. And from this word equation, we see that this stickiness factor is equal to the ratio of the magnitude of the maximum force of static friction to the magnitude of the normal force. This ratio has units of newtons over newtons, which cancel out, so the ratio has no units and no dimensions. This ratio is just a number. And we call this ratio, this number, the coefficient of static friction for a given combination of surfaces. And for short, we represent it by the Greek letter mu, with a subscript s for static. As an aside here, let me introduce you to mu. Here it is. It's written mu and pronounced mu. It is the Greek version of m. And take out your handwriting copybooks, please. And like in grade school, let's practice drawing some mu's here. A and B and mu, mu, mu. To me, it looks kind of like a pointy M or a U with a trunk, always like a little elephant maybe with a trunk coming out there. Pause the video and practice your mu's. Got it down? Great. So every combination of surfaces has its own value of the coefficient of static friction. And because it involves the complex surface chemistry and microtopography of the two surfaces, it's basically impossible to theoretically predict ahead of time what the value of mu(s) will be. This has to be determined empirically. Empirical, it's my favorite word. Empiricism is what makes science science. Empirical knowledge is knowledge that's gained through observation and measurement. So someone has to actually measure mu(s), and such an experiment might actually look like this. Here's a simple version of an experiment that could be conducted to determine the value of the coefficient of static friction for concrete on wood or for concrete on rubber. Here we have two experiments, a concrete cinder block placed on a wood surface and then placed on a rubber surface. Initially at rest, and then we pull on it with a rope to the left. We pull on it, gradually increasing that force of tension until the cinder block begins to move, until we break static friction. So if we measure the force of tension in the rope as we pull harder and harder, then just at the moment when the block first slips, just at the moment we break static friction, at that moment we know that the tension is equal to the maximum force of static friction. So if we measure the tension at that last moment, then we know the max static friction. And then if we take the ratio of the maximum force of static friction to the value of the normal force, which we know will be equal to the weight of the block, then that ratio is exactly what we mean by the coefficient of static friction for these two surfaces. So you put a cinder block on wood, and if the cinder block has a weight of about 120 newtons, you'll find that you have to pull with a force of at least 72 newtons to get that cinder block to move. 72 is about 60% of 120, indicating that the coefficient of static friction for concrete and wood is 0.6. Rubber and concrete are much stickier. That same concrete block, that same cinder block, you would have to pull it with a force equal to about 120 newtons, which is the weight of the block, before the block starts to slip. So sticky is rubber on concrete. So that ratio of 120 to 120 is 1. That's about as big as you ever see for a value of coefficient of static friction. This is about as sticky as surfaces tend to get. Okay, so our general equation here for the Coulomb model for maximum static friction can now be written down. We look at this relationship, this ratio, and just rearrange it to move the normal force up here by the coefficient of static friction, and we have this. One can calculate the maximum force of static friction on an object by taking the coefficient of static friction for the two surfaces and multiplying by the normal force being exerted on the object. If you look carefully, you will see that there is a hidden message in this equation. I'll reveal it at the end of the video. See if you can spot it before then. So experiments like these have been conducted many times. So generally, when you need to know a value of a coefficient of friction for some common combination of surfaces, you look it up in a table. Tables like these. I grabbed these two tables from two common physics textbooks, Giancoli and Knight, and you'll see common combinations of materials here, and then a column for coefficients of static friction, also columns for the coefficients of kinetic friction, and something called coefficient of rolling friction. We'll discuss those in another video. But by examining this table, you'll see that mu s is always a positive fraction by definition, and it's usually between 20% and 100%, or 0.2 and 1.0. That means usually max static friction is less than the normal force, because mu is usually less than 1. But note that there's no reason in principle that mu couldn't be greater than 1. In that case, max static friction would simply be greater than the normal force, which could be possible for some hypothetically extremely high friction materials. Alrighty, after the last few videos, you should be able to do the following. Think about these 4 tasks, and if you know how to do them. You should be able to calculate the value of the force of static friction on an object if that object is subject to some applied force that's less than the maximum value of static friction. Also calculate the force needed to break static friction. Calculate the maximum no-slip acceleration of an object on a tray, and describe a specific reason why rubber tires are preferable to wooden wheels. Okay, so about our equation here for maximum static friction. Did you see the hidden messages? It is, of course, that friction is